In this lecture, we're going to introduce the rigid body equilibrium conditions and identify support reactions on the rigid body and draw a free body diagram of the rigid body. First, let's recall some idealizations we made and we're using in this course. First, we learned particle equilibrium. An object can be modeled as a particle when its geometry or dimension are negligible for the interest of the study. So particle can be big, can be small, as long as the geometry or dimension is not important for the interest of the study, then we can simplify the object as a point. That will be the particle. Now from today, we're going to learn equilibrium for rigid body. So the rigid body is when the shape of the body does not change, even if a load or more loads are applied. So a rigid body not only has mass, but also has dimension and geometry, but it will not deform. So that's why it's called rigid body. The shape does not change. So think about a diamond. Let's record the conditions for particle equilibrium. According to Newton's law, an object will have a zero acceleration when there is no unbalanced force acting on it. In other words, the resultant force, Fr, in vector form, equals to the sum of all the forces should be 0. Since particle is an idealized object with no size or shape, so it's only represented by a dot in space, the force acting on the particle will be concurrent, which means there is no moment about the point. So for a 2D problem, the vector equation can be written as two scalar equations, that the resultant force in the xy direction must equal to 0 respectively. For 3D, the vector equation becomes three scalar equations. And we only need to make sure there is no resultant force. We don't need to consider the condition for the moment. However, a rigid body has shape and size, and it may not be static even if the resultant force acting on it is 0. For example, consider the moment of a couple. The two forces acting on this wheel are in equilibrium, but this only means that they don't cause translational motion because the resultant force is 0. But the two forces make a couple moment which has a magnitude of F times d. That is a free moment which will cause rotational effect of this wheel. Therefore, for rigid body to be in equilibrium, the resultant external force and resultant moment must be 0. For a rigid body to be in equilibrium, the net force as well as the net moment about any arbitrary point O must be equal to 0. So those two equations need to be satisfied at the same time for a rigid body to be in equilibrium. So the first condition means this rigid body doesn't have translational motion because force will cause translational motion. And the second equation, we need to choose any point in space as a reference point to calculate the moment about that point, and moment about this point including the moment caused by all the forces and the couple moment. Thus, the sum of the moment should be 0 for the rigid body to have no rotation. So when we have a rigid body equilibrium type problem, no matter we have a 2D problem or 3D problem, we always have the two vector equations, one for the force and one for moment. But if we have a 2D problem, and based on one free body diagram, we can write a maximum of 3 independent scalar equations and solve up to 3 unknowns. And generally, this is the set of 3 equations, scalar equations, that we're going to use to solve the equilibrium problem in 2D. We will have sum of the x direction forces is 0, and sum of the y forces equals 0, and one moment equation about any arbitrary point O. But there are alternatives as well. Depends on specific questions and information. You can choose other scalar equations. So again, keep in mind this set of equations, 2 force equations and 1 moment equation, is the most commonly used set of equations, but they are not the only set of equations that we can use. Sometimes we may choose 1 force equation and 2 moment equations, or even 3 moment equations. The key point is here is that we can only write a maximum of 3 scalar equations. Of course, for each free body diagram, you can write many equations, especially for the moment. You can choose different points on this body and to write moment equations. But keep in mind, those equations are not independent equations. You can transform one equation to another, or convert one equation to another, or combine 2 equations to get to the 3rd equation. So again, you only have, or we can only write up to 3 independent equations for a 2D rigid body equilibrium problem. Now let's take a look at what kind of problems we're going to solve in this chapter and the following chapters. So here's one example of rigid body equilibrium problem. Normally, the applied loadings are known. So we have one concentrated force. We have distributed load. We have, this is the couple moment. Since couple moment will only have rotational effect or moment effect, there's no net force, so couple moment will be placed on the structure as a moment with rotational directions, with given rotational directions. And what are we looking for? We're looking for support reactions. For example, this beam now is built into the wall. And to keep this beam in static, what kind of reaction the wall should provide? Are there forces? Are there moments? If there is force and there is moment, what's the magnitude and what is the direction of those support reactions? So to do that, we will need to first identify what kind of reactions are associated with different types of supports. Let's use this example to see what kind of support reactions the wall will provide to this beam so it stays static. So this wall is considered as a fixed support because the beam is fixed here. It doesn't have any type of motion. No translational motion in any direction. There's no rotational motion as well. And this is a 2D problem, and usually we want to set up the XY coordinate to describe the direction of the forces. So first, if we take a look at this concentrated load F, we can resolve it into 2 components. One is along the X direction, one is along the Y direction. Now, this F of X pushes the member to the left. Therefore, the wall must exert a horizontal force to the right in order to prevent the motion to the left. So if I call this point A, here is a component pointing to the right, and usually we call this force AX. Same way, because of the horizontal component of this force F, the Fy, as well as the distributed force causing the member to go down. So the wall must exert a vertical force up in order to prevent this downward motion. So that means there's another component applied on point A of y pointing in the y direction. And finally, this force F, especially for the Fy component, will create a clockwise rotation moment about point A, and also this couple moment also cause the member to rotate clockwise. So the wall also must exert a moment support that is counterclockwise in order to prevent this rotational motion. So this, we'll call it MFA, the moment. So since this is a 2D problem, all motions can only occur within the XY plane. So there cannot be any other type of motion. And those three reactions are the support reactions from this wall or from the fixed support. A few example sets of diagrams are shown here. Other support reactions are given in your textbook. I will also post it in Canvas, so if you want to check your understanding of support reactions and to identify certain support reactions, you can check the table. But the rule of thumb to identify support reactions are as follows. If a support prevents translation of a body in a given direction, then the force is developed on the body in the opposite direction. For example, the roller support here, this structure is resting on the surface. Without the support, because of the gravitational force or the weight of the structure, it may sinking down to the surface. So to prevent this type of translation of the body, the surface must provide an opposite force to prevent it from going into the surface. Therefore, a force is here pointing to the opposite direction to prevent the structure from going into the surface. And keep in mind, this support reaction or the force is perpendicular to the contacting surface. So this is the 90-degree angle. It's not perpendicular to the structure, okay? But it's perpendicular to the smooth surface the structure is resting on. Same idea for the fixed support we just did. Because the wall prevents the beams from going into the wall, so it will provide an opposite force to push it out. And it also prevents the beam from going down the wall, so you will provide an upward force to push it up. And the second is, if rotation is prevented, a couple moment is exerted on the body in the opposite direction. So same idea for this fixed support, because without any support, if you just have a beam, you will have a clockwise rotation. So the wall must provide a counterclockwise rotation to balance it out, so this beam will stay in place. And another generally or commonly used support is this smooth pin support. A smooth pin will have two support reactions, two force support reactions. One is along the x direction, one is along the y direction. Because the pin allows the structure to rotate about it, so there is no moment support. It won't prevent rotational motion, only translational motion. So there are only two force components. Let's use this example to see the procedures of analysis. Determine the support reactions at the fixed support A. 3 major steps to solve a rigid body equilibrium problem. First, if not given, we can establish a suitable XY coordinate system so we can describe the directions and the forces easily. And second is to draw the free body diagram. And third is to write the equations of equilibrium. So actually, the similar approaches we did for the particle equilibrium problems. The only difference is maybe the free body diagram is a little bit more complicated. So let's take a look at how to draw a free body diagram for a 2D rigid body. First, let's establish the XY coordinate axis like this. Usually X will be in horizontal direction and Y will be in vertical direction. Just occasionally, if your structure is oriented in a different direction in space, maybe we can build up an XY axis in a different orientation. But commonly, we will just have X and Y look like that. And second, we're going to remove all the supports and draw an outlined shape of the body. So now in this case, the support is the fixed support, the wall here. So we're drawing the free body diagram of the beam. So we're going to remove the wall, only leave the beam, isolate the wall from any supports. And then we're going to note all the external forces and moments on the diagram. So first, there is a couple moment. So we're going to draw the couple moment is a clockwise couple moment with the magnitude which is 200 Newton meter. And then we have this concentrated load, distributed load. So usually when we draw the free body diagram, we're going to replace the distributed load with a concentrated load. So now the concentrated load, right? The magnitude of it will be the area under this area of the rectangle. So we can do the calculation on top of here. 80 times 80 Newton per meter times 1.5 meter, which will be 12 Newton, and located in the middle of here. So this is 12 Newton. So we're going to place 12 Newton directly on the free body diagram, and it's pointing down in the negative y direction. And we're going to put dimension later. Next, we have this 1,000 Newton concentrated load. We also want to place the dimensions of the body because we need to use it to write our equations, especially the moment equations. So this is the point A, and this point A to the concentrated load, we can do a little bit of math, right? So because the concentrated load is 0.75 from the left side of the distributed load. Sorry, I'm talking about distributed load here. Okay, so it's 2.75 meter from point A, and this concentrated load is 4 meters from point A. And don't forget this slope triangle, because we can resolve this force into x and y component. Again, it will be easier to write equilibrium equations by doing that. Okay, don't forget we're looking for support reactions at point A, and the support reactions are also external force, because it's acting on the body from outside. So it's also external force, and we're looking for the magnitudes and directions of those. So now we're going to put, this is the fixed support. We already analyzed for fixed support, there is one x component, AX. There's one y component, A of y, and there is a couple moment, which will be counterclockwise couple moment, MA. and we are looking for those values. So when I draw the free body diagram, you see I usually use different colors, and my suggestion to you is you can do the same thing. The forces in red, for example, will be unknown values, the values I'm looking for. And in black colors, that means those are given values. Also, you can resolve this force constant to the load if it's not pointing directly into X or into Y. You can resolve it into X and Y component when you draw this free body diagram. So we're going to replace this 1000 Newton force by the X and Y component with corresponding directions. So the X will be pointing to the next direction of the X with the magnitude of 1000 times 3 over 5, right? So that will be 600. And the downward force is 800 Newton. And this is my free body diagram. Double check the forces to see if do we have all the forces we supposed to have. We have one couple moment, we have this constant distributed load replaced by one concentrated load, and we have another concentrated load. We have 3 support reactions, and those are the values we're looking for. Again, recall we said for a 2D rigid body equilibrium problem, we can write 3 independent scalar equations, so we can solve up to 3 unknowns, and we have 3 unknowns over here. Therefore, we can find all of them by using this one free body diagram. So next, let's apply equations of equilibrium to solve them. The first equation will be sum of Fx equal to 0. So we just need to gather the forces pointing in the x direction. So we'll have first Ax, which is the positive, pointing to the positive direction. And then we have another one is the minus 600 Newton, which is the x component of the 1000 force, Newton force. And those are the only 2 forces in the x direction. And this equal to 0. From this equation, we already can solve A of x. So A of x is 600 Newton and pointing to the right. Second equation we're going to use will be sum of Fy equal to 0. Same idea, we're just going to gather the forces pointing in the y direction. So we have A of y pointing up, so it's a positive, and we have this 12 kilonewton pointing downwards, so minus 12 Newton, sorry, it's not kilonewton. And we also have this 800 Newton force pointing down, and that will be it, right? And in this equation, we again just have one unknown, which is A of y. So we can solve AY directly. So first, let's establish the XY coordinate axis. So usually x will be in the horizontal direction and y will be in the vertical direction. Occasionally, maybe it's easier to build your x, y in a different orientation, given if your beam is directed in a different direction in space. But in most of the cases, x and y will be like this. And next, we're gonna remove all the supports and draw an outlined shape of the body. So keep in mind, we are drawing the free body diagram for this beam, and we're looking for support reactions from the wall. So we need to remove everything, all the supports from the beam. So we're gonna isolate the beam from this wall, but only place support reactions to the beam. So now let's draw the outline shape of the beam itself without the wall. Next, we're going to show all the external forces. So keep in mind, for the free body diagram now, we're doing external forces. The force is applied on this beam, not within the beam. So let's just place those forces already given. The first one is this couple moment. Okay, couple moment is also an applied force on it, and magnitude is 200 Newton meter. And move to the right, we have this distributed load, which has the loading intensity of 80 Newton per meter. So when we draw the free body diagram, we usually replace this distributed load with one concentrated load. So now the magnitude of this concentrated load will be 80 Newton per meter times 1.5 meter. So the magnitude will be 120 Newton pointing down, and the location of this force is in the center of this geometry, which means it's halfway from the left end of this distributed load portion. So it's 0.25 here. All right, so I'm gonna just put this concentrated load on my free body diagram. So I have the simplified version of those forces. So its magnitude is 120 Newton pointing down in the negative y direction. And lastly, we have this concentrated load of 1000 Newton and with a direction triangle given. So this is 1000 Newton, and don't forget the direction or the slope triangle to help us resolve the force into x and y component. And also to make the solution easier, or for it's easier to write the equations of equilibrium, usually I will place the force, or I will resolve the force if it's not originally pointing to the x or y direction. I will first resolve the forces into x and y direction. And since this one is pretty simple, it has this slope triangle, so we'll have this x component pointing to the negative x direction and y component pointing down, given the original direction here. And using the slope triangle, the x direction force will be 600 newtons, which will be 1000 times 3/5. And the y component will be 800 newtons, which is 1000 times 4/5. Right? All right. So those now are the given external loads. And don't forget, we also have the loads we're looking for, which are the support reactions. After we removing the wall from point A, we have to replace it by the loads by the support reactions provided by the wall. So we already analyzed the support reactions by this fixed support. There will be a x component, prevent the wall from moving to the left, and there will be a y component, preventing the wall from moving down, and also there will be a couple moment, counterclockwise couple moment, prevent the clockwise rotation. So we have three unknowns. And note that usually I have different colors on my free body diagram to remind myself what values are given and what values are not given. The values we're looking for are here. So we have three unknown values, and we have three independent equations for a 2D rigid body equilibrium problem. So three equations, three unknowns. So that means we have enough equations to solve them. Another important thing when you draw the free body diagram is the dimensions. We want to indicate the dimensions of the body because we need them to write the moment equations. We need those distance for moment arms, right? So first we need this distance from point A to the concentrated load, the 120 Newton concentrated load. So distance will be 2.75 meter. And next we have this concentrated load, which is the 1000 Newton concentrated load. So it's 4 meters from the point A to this concentrated load. And now this free body diagram is complete. Then second, using the free body diagram to write equations of equilibrium. The first equation will be sum of Fx equal to 0. So we just need to gather all the forces in the x direction. So the first one we have will be the A of x is pointing to the positive x direction. And then we have another one, which will be the negative 600 Newton pointing to the negative x direction. So that's why it's negative 600 Newton. This equal to 0. So that means we can already solve this A of x, and A of x itself to be 600 Newton from this equation. And next, we're going to write the equation of sum of Fy equals to 0, and we only need to gather the forces pointing in the y direction, horizontal directions. Ay, that's the first one. And the next one will be a negative 120 Newton because it's pointing to the negative y direction. And the third one is negative 800 Newton. And those are the only 3 values we have along the y direction. Again, there's only one unknown value in this equation, so we can solve A of y from it. And A of y will be 920 Newton. And the next equation will be a moment equation. So which point should they choose to create the moment equation? We said we can find any point and write the moment about that point. And no matter which point we choose, the resultant moment should be 0. Because this beam doesn't rotate about any point. There's no rotation at all. So any point you choose in the space should have the resultant moment of 0. So the question is, which point should we choose? Should we choose the point here, or should we choose point here, or any point here, or here, or here? Well, the answer should be point A. Because point A, or the force AX and AY, the annual forces are concurrent about this point A. In other words, AX and AY has no moment about point A because the moment arm is 0 because of the line of actions passed through this point A. Therefore, they will not appear in the moment equation. So that means even if you made mistakes in your calculations for AX and AY, it will not affect your moment equation. So that's kind of the approach or the strategy. When you write this moment equation, you want to choose a point that has most of the forces or even most of the annual forces pass through it. Then those forces will not appear in that moment equation. So now let's write the moment equation about point A. So again, don't forget to define your positive moment. So counterclockwise is positive. Sum of the moments about point A equals to 0. So the first one we have is MA. That's a couple moment. That's the unknown, MA, and we define it as, we assume it is counterclockwise rotation. And next is the 200 Newton per meter or Newton meter couple moment. So again, recall that we said couple moment is a free vector. Even if it's not located on point A, it has the same moment about point A, or the effect about point A is the same. So we want to put this 200 Newton meter into our equation, but it will be a clockwise moment. So it's negative minus 200 Newton meter. And the next one will be the 120 Newton. It also creates the clockwise rotation. So this will be 120 Newton times 2.75 meter is a minus. And lastly is the 800 Newton, because the 600 Newton X force, X components also pass through point A. So it doesn't have any moment about this point A. So it will be minus 800 Newton times 4 meter. And this should be 0. In this equation, we again just have one unknown value, and we can solve this. A is 3,730 Newton meter. And with all three values being identified, the problem is solved.